What we're going to do now is give you a quick update on our Brain Impact Simulator from Microsoft Hacking STEM. And this Brain Impact Simulator is so that we can measure the impact on our fake brain that we've made out of a balloon with jelly inside. And we can do this by using our Velostat resistors, or variable resistors, or sensors in this case. And that's because Velostat is a material that is an insulative material, which means it doesn't allow electricity to flow through in its normal state, but when compressed, it does. It allows carbon particles, which are within this polymer, to align and create an electrical path for electricity to flow. And that means when we connect our positive and negative sides of our sensor, we can then have electricity flowing through, and we can actually take readings of those variable resistances. How we do this is by using Ohm's law. We create a circuit and we adjust the resistance. In the case where we have no force applied to our sensor, the resistance is quite high, or in fact it's much higher than 100. It's probably infinite because it's or closer to infinite because it's an insulative material. As soon as we apply a force, we have a low resistance, and that allows more current to flow based on Ohm's law. Given that we have 3 volts from our microbit, V equals IR, we can see the formula is 3 volts equals current times whatever the resistance is. From the calculations, we see a high resistance leads to a lower current than if we have a low resistance, we have a higher current. Pretty simple in terms of the mathematics behind it, but that's how we are going to end up with varying results in our Excel spreadsheet. How we actually connect it is connecting our microbit to an edge pin board that connects straight into our breadboard. Alternatively, we can use an expansion board or an Arduino that will do the same thing as well. How breadboard works, if you haven't seen before, is that it has metal conducting strips underneath the face on the top. If you take them off, you can actually see that these strips on the side go all the way down, so anything connected at the top will also connect through to the bottom. Across the center, we have much shorter rods here, but that just means that we can drop in pins without the need to use alligator clips or solder, and it really reduces the complexity of any kind of electronic testing. So what we're going to do is I'm going to show you how we actually connect this in TinkerCad circuits, so you can actually have a play with it before it actually gets made as a prototype device. Now if I bring it over here, I've set up on TinkerCad circuits, I've simply gone through and found some of the microbit components. I've brought in a microbit breakout board. I've found a resistor, which is the same as a Velostat resistor. If I search resistor, I've got to take it out of here and go to all components. If I search resistor, I should be able to find a force sensor. And then I've aligned them so that I've rotated using this button in the top left corner. And then simply by clicking on a pin, you can actually make connections between your force sensor terminals and the breadboard. Now that's all pretty straightforward. We can change the colors of our wires. That'll make it a bit clearer as well. But I'll go through how I've actually connected it and some of the basic code that I've included as well. What I've done, like I said, is I've connected our ground. So that horizontal line there connected to this, or that vertical line there, connected to one of the pins in the negative terminal row. I've also connected the 3 volts to one of the positive, and therefore I've electrified these two rows. All I need is to create a circuit around them. That circuit is our force component here, or our Velostat sensor. A resistor to which just aids in our calculation, so we have a baseline to go from. And in the case where we have no resistance, we wouldn't want a short circuit, so I've got a resistor there as well. And I'm just going to use 100 ohms as well. And now we've got a circuit here that connects our positive and negative, so we can actually see the amount of current flowing through. How we see that is by connecting this 0 terminal, the P0, into that circuit. And all of a sudden we can take readings. And I've done that again with the second pin, or pin 1. I've just got this circuit here, and we're connecting that to our pin 1. What this looks like in terms of the code is pretty straightforward as well. Now over here I have on button A press, so when I click the A button, it's going to show a number, and that number is going to be the analog reading of pin 0. Now the analog reading is a scale between 0 and some undefined number at this point, but it means it will give us a reading, a variable reading. So if we have more current flowing through, it could go up to 100, 200, 300. If this was a digital reading, it would give us on or off. It's only going to give us two options. And what we really want is an analog reading. Now, if I run simulation as we press here, run simulation, I then have to press the A button. And at the moment, there's no current or voltage or no current flowing through. And that's because the resistance of this velostat sensor is infinite, essentially, because there's no force applied. If I apply a force, if I go to say 5 newtons, which is about half a kilo, I should get a reading of, there we go, 49. If I was to raise it to 10, it should be even higher again, so 79. All of a sudden, you can imagine how if we connect 5 sensors along here and we have different forces applied to each, and forces that aren't consistent, if we take a live reading, we can actually see that we might end up with something like this. And Microsoft Excel has a live data streamer, which allows us to see that live data as well. That's going to be the next stage of this process. But for now, have a go at connecting each of your 5 sensors, just like this one here. This one here, I've connected in, I've got to stop simulation. I've connected in a way just to test out an LED to also show you what this might look like. Start simulation. If I apply a force, it allows more current to flow, and we can get our brightness going up as well. But in this case, all you need to do is replicate how these pins are connected, or how these sensors are connected to pin 0, 1, 2, 5, and 8. And then you can have 5 sensors ready to go and replicate this in the real world so that you can have a brain sensor ready to test out with some impact forces. Good luck. See if you can connect the other 3. I'll leave this in the comments of the video so that you can experiment with this particular base breadboard.